Greetings everyone. Today we are starting a big major chapter in our quest for learning basics of artificial intelligence. We will talk about machine learning. So this is chapter 19 on the book Artificial Intelligence, a Modern Approach, 4th edition, the US edition. So today we will talk about what encompasses the major categories or major classification, how we classify machine learning. And pun intended, classification is one of the actual ways of classifying things, actually. So that's a pun intended there. So we'll talk about supervised learning, unsupervised learning, the need for training and test data, the need for data processing, but in due order. So a lot of concepts to learn, and maybe if you have time also I'll show you some practical examples. If not, we will have some time for yourself, some supplemental notebooks. So again, how do we consider, when are we learning? If we are a human agent, right, we improve our performance after making some observations on the world, right? So maybe we create a shopping list, maybe invent a new theory of universe like Albert Einstein, right? So a broad spectrum of learning, right? Simple tasks or complex theories. So machine learning is basically learning when the agent is, well, computer-based, right? So the core idea is, of course, that there's going to be some data, some observations, and the model is going to be learning, right, in order to make predictions. So again, there are two main reasons why we need to, why machine learning can be useful. So when we are designing some sort of system, informational system, something bigger, we cannot foresee everything possible, right? We cannot make rules for everything. So we want to make something general, right? Something that generalizes well, meaning we cannot predict the future completely. We have real world systems they are not completely, how should I say, enumerable, meaning you cannot predict everything, right? You cannot enumerate rules, basically. So we need sort of system or agent to be learning, improving performance. Also, of course, some things like facial recognition, which is very well solved problem in machine learning these days for most things in last 10-15 years. So it used to be that we thought that the way to do this was to make explicit rules about how to recognize face. This has progressed up to about 2012 or so. And well, it turns out that the machine learning approaches, which are not rules-based but learning from the database, are actually perform better. So these machine learning algorithms offer a viable approach for these approaches when we have quite a bit of data, right? But again, we will see this. So we'll look at various methods. Again, this will be a very brief overview. So a lot of these algorithms, of course, are quite involved. So we'll only touch on the basics, right? So basics are, statistical models, right, most of these models are based on statistics. Machine learning also closely related to something called data mining. Many of the algorithms actually in machine learning also are used in data mining, which sort of was popular maybe about 20 years ago in early 2000s. Now machine learning has taken over. So again, oftentimes when we talk about AI in a common use language, people actually are thinking about machine learning. Again, as we know, you're now smart, you know that AI is not all machine learning, but machine learning is the majority of getting the majority of the press, so to say, right? Including, of course, any of the large language models. Those are a type of machine learning. In fact, they are classifiers, just to give you a little taste of what's to come. So, right, so what is machine learning, basically? We rely on patterns from some data that we are supplied, right? The core idea is the rules are not written explicitly, meaning if-else statements for doing something are not built before, loops and things like that, right? But the actual model is built from some sort of data. So then we have to think about how do we divide these tasks? And so there are a couple of major ways of dividing this. So supervised learning. So this means that we have some answers. We have answers, labels, meaning we have training examples, meaning the data we are given, or maybe we obtained somehow ourselves. There is some sort of output value or multiple values, labels, right? So then the model learns, makes predictions based on this input data. We will see there's a way of dividing this further into classifiers and regression-based models based on what type of data we are predicting. But for now, that's enough. Also, unsupervised learning. So if there's supervised learning, there's unsupervised learning, meaning we don't have any answers. We just have some data points, maybe it's just single, one-dimensional, two-dimensional, multi-dimensional data, right? But so what can you do then, actually? It turns out we can try to find some patterns and relationships, sort of explore, or what we usually call this clustering. Generally, we mean clustering by unsupervised learning. So then you have this sort of hybrid category, semi-supervised learning. Again, one of the core I would say tenets or the pain points in machine learning is there's never enough labeled data, right? So machine learning researchers use all kinds of tricks to generate this sort of, I wouldn't say fake it, but sort of hybrid approaches, multiple approaches. So there is partial label, meaning there's some data we have answers for, some we don't, but we want to use all of the data. So somehow we want to extend this data, so various tricks for that. And then there is something called reinforcement learning, actually, right? In fact, heavily used in modern LLMs, because it turned out just a pure classifier by itself is not enough to make something very humanly pleasable. So meaning there are sort of like, there is sort of carrot and stick idea, right? There's a way of nudging models towards some goals. And let's talk about some of the typical vocabulary you will learn in this. You will encounter this over and over and again as you go on your machine learning journey, so to say. You'll see this again. So data set, of course, is what we are going to be learning from, right? And again, typically we will divide this into training and testing sets. We'll talk about this in a moment. So features, what are features? Those are the incoming variables of dataset, meaning those are the characteristics. Age, name, length, coordinates, time, whatever you want to call it, stock price, whatever, all those could be features. Also, some of those could also be labels, meaning if you want to use one of these features, well, generally labels are separate, right? But theoretically, of course, we could say one day somebody's one in the same data set, you can of course say, okay, we want to predict price, or maybe you want to predict weight. I mean, so back and forth, right? At one moment this could be a feature, next time it could be a label, right? However, of course, when we are actually training specific model, we divide this, right? Labels are separate from features, right? We separate it, right? Labels are generally what we call y, right? Just like in a function. Features are generally major X. I should probably mention this, right? So we often called X, right? So to signify multiple features, right? Big X, right? Labels, single column labels are often marked Y. Again, I'm sure if you're remembering your grade school algebra, you can figure out why that's the case, right? X and Y, so it makes sense, easy to understand. In comes X, out comes Y, right? So model is this mathematical representation. So it's trained using these algorithms on this data set, and that's what's going to provide our answers. So training, right, machine learning, when you train a model, right, you sort of algorithm, whatever the algorithm is, it takes in this incoming data, right, and, well, it is being fitted. It is being fitted, right? So at some moment, well, it starts to it becomes able to make predictions. So, and then we talk about inference. In fact, again, when we are using large language models, you know, we are, as a users, we are always doing inference, basically, right? We are not training. Well, we actually could be applying some training data to the providers, but technically we are doing inference, right? So when we are obtaining answers, when you're generating some pictures, right, so and so on and so on, well, it is actually inference, right? Training is much more, generally, much more intensive process. Right, so we get the answers. It might take, of course, for serious models, could take maybe multiple months to train, but only a few seconds or maybe less than a second to get the answer, right? So, and then we come to one of the core ideas behind this is there's this famous saying by statisticians, again, if you're taking statistics, you probably might have heard it, that all models are wrong, but some models are useful. So that's the core idea behind machine learning. So, again, the models by itself, whatever we are modeling, right, atomic system, planetary system, whatever they'll model, right, as we all know from Newton, right, his model was not quite correct, right, until Einstein, and also Einstein's model is not quite correct, but they are quite useful, very useful, right? So, again, so it is machine learning, right? You will never get, well, a perfect model doesn't really exist as such, right? It's because in order to be usable as a model, by definition, there has to be some sort of approximation, some simplification of whatever it is modeling. Otherwise, it would not be model. So it's sort of a tautology in a way, right? So, let's look at some common algorithms. Again, we will see these. Maybe we'll have some time to look at these in a live codebook. This is just a quick overview. There is a linear regression. This is used for predicting continuous value. There are some logistic regression used for binary classification tasks. By the way, then there are decision trees, which can be used for classification or regression. So, meaning again, what is classification? Predicting something in discrete values. What's the regression? Continuous value. So, like a floating point value. So think of this like, so these are like a apple, banana, yes, no, those kind of things. Buy, not, but however, continuous value, things like price, weight, things like that, which have a floating point value. So those are the easy way to say. Regression, so classification and regression as a sort of regular regression. So decision trees. So decision trees can be used for both, actually, very commonly used, and one of the rare types of machine learning algorithms that can actually be visualized by human beings. So we come to another sort of takeaway from all of this, that so I should mention this, right, one of the rare, right, decision trees are one of the rare type of ML algorithms that can be visualized by humans, right? So very rare, actually, yeah. So that's one of the most things, unfortunately, in as far as machine learning algorithms go, they are sort of function as black boxes. Meaning we can analyze the inputs, outputs, we can measure how well we are doing. However, we cannot completely understand these algorithms as far as the exact way they arrive at the answer, because what they are trying to do is, well, provide some non-linearity, right? So neural networks, those are extremely complex. So again, pretty much, I would say, well, we can have some very simple neural networks, but generally you cannot be able to understand the actual process. You can see the building blocks, so to say, right? But they become extremely complex itself. Even though the model itself, the architecture might look very simple. Okay, so yeah, so the thing is, we do need to have some evaluation metrics. So that leads us to the fact that we need to figure out how well are we doing. Otherwise, we'll have a problem that basically, if you have a black box, well, then you can't really do anything good, right? So typical problems, there are two types of problems with machine learning models. Overfitting, probably more common, meaning we supply so much data and the model learns exactly what the training data supplies, the answers. So it works perfectly on the training data, but poorly on some data that is not seen. So basically, it's like memorizing, yes, if it's red, buy an apple. If it's green, buy a lime, right? Some rule, basically, sort of like a clever horse or something, right? A circus animal, basically. Well, luckily we don't have circus animals anymore, right? But in general, right? So it's mimicking basically the really overfitting model, right? It knows exactly what to say, what training data. But however, the worst overfitting models don't have any idea what to do when they are supplied with unknown data, right? So that is, of course, the issue, right? And this is one of the typical stumbling blocks for beginners learning machine learning. Underfitting means maybe it's just a very basic, we don't have enough information, maybe it's too simplistic, right? That's also a problem. So it's always sort of fight between overfitting and underfitting, right? And then we come to other things we do when we are learning, improving our models, such as feature engineering, meaning we don't have enough features. Maybe we can somehow figure out something. Maybe we have features, but they're not supplying good information. We can supply engineer features out of existing features. Like maybe a simple example, you have a first name, last name features, and you can obviously trivially make a new feature called full name, right? Or maybe you can have some fitness metrics features, and you can make a new feature which says overall fitness, right? And sometimes these things, it seems like you're not adding real new information, but they actually can make a difference, especially the numerical ones, right? Also, oftentimes when making a model, you need to deal with regularization, various techniques which deal with to prevent overfitting. Also, very often you will see this something called hyperparameter tuning. Again, what this means we are adjusting settings of the algorithm. Most of the algorithms have some sort of, you can think of them as function parameters, meaning sort of levers we can push back and forth to make our model perform slightly different, right? And in fact, that's why pure mathematicians are not very fond of machine learning engineering, because it seems like a lot of this is sort of like slightly stumbling in the dark. Well, knowing some ideas, you have some lights, but you maybe you are maybe a little bit like a drunk guy looking for keys under the light when you should really lose the keys in your house, right? Sometimes, to make an analogy, right? So, okay, so there are lots of different learning, right? So again, machine learning can become useful. So different learning. Let me see this here. Is we can perform direct mapping from state conditions to actions. We can infer world properties from perceived sequences. We can understand how the world evolves on the outcomes of actions, and so on and on. Right? I'm not going to read them all, but basically we can. All of these components can be learned, actually, right? In agent design, all of these steps can actually be part of the learning process, actually, right? For example, a self-driving car, right? Human driver may learn when to brake, learning from observed conditions, maybe recognize buses from camera images, right? Learn effects by experimentation, right? If you push this gas, you go faster, right? Maybe your passengers are starting to scream, right? So that's also a feedback, right? So yeah, so that's sort of a crazy example, but that's what I'm talking about right now. So again, so supervised learning, I mentioned this, right? Let me see here, right? I'll show you a very simple example. So we have some data points, right? So we are building a model. So these points represent a data set, right? So, and we can generate some plots, right? Here, right? So we can do a line. This is very well known for already over 100 years way of doing. We can figure out a function, a linear function, kx plus b, right? Or ax plus b, right? Intercept and coefficient, right? And draw a line through any points to minimize the error, right? So those are the most common type of regressions. You can also drive a sinusoidal. Find the sinusoidal way which best approximates these data points. And you can also make a function like this. Draw lines between points. That's also a function. So this means, so what's the idea? This means if there's new data come in, maybe if there's a point here, you can make a prediction. This model will predict data is here, this model will predict here, and this model will predict here, right? If you have some point here coming in new x, right? Well, how about this one? This is degree 12 polynomial. This actually fits perfectly, probably, well, fits probably the best. Well, you can say piecewise linear also seems to fit best, right? However, both these models have the problem that, well, they are very heavily tend to overfit, especially this. This is degree 12 polynomial, meaning it's x to the 12th power, x to the 11th power possibly, and so on. And you can see the problem why overfitting exists. Because what happens if you have x here? Well, you will have a overfit. Your model will be making a really bad prediction, right? Because it's unlikely that real-time data, this dot is going to be here, right? It's probably around here somewhere. We don't know. Again, this is, data usually does not have these huge outliers in this term, right? So you cannot predict those outliers generally, in fact. So that's the idea of regression, right? So this is what type of task? Supervised learning, right? We have some incoming data, and we are trying to make predictions, right? And we basically should try to choose best hypothesis. And again, one of the core ideas comes from our old friend Occam, from 13th century it was, I think, Occam's razor. You might have heard of him, right? His idea was that it goes through for many areas of life, including machine learning. All things given being equal, choose the simplest model, meaning use the least assumptions, right? Do not add unnecessary complexity, well, unless it helps, right? So here, right, so that's the thing. There's always trade-off, right? So, again, fancy models, well, have a higher tendency to overfit. So, yeah, now we come to another example, right? We have some, this is example of restaurants. The book gives you another book example. Do you want to wait for a restaurant, a table at a restaurant? And you are given a whole bunch of data, actually. Maybe I'll have it, I think I have it here. Yeah, I do. Right, here is some data. Yeah, this is from the book. Right, and you have some input variables, right? So these are x1 up to x12, right? Actually, so alternate, yes, there's the bar, it's Friday, no, yes, hungry, are you hungry or not? Are you patrons? Is there some patrons or not? How price? Is it raining or not? Forgot what the resident was, what type of food it is, and how long to wait. And then these are the data sets. So this is a training set, because why? We know the answers to what happened. So given these data points for this particular restaurant, what did the couple or a person or whatever it was used in training do? Did they wait or not, right? And our goal is, so that's why, not this why, right? So our goal is to see if maybe we have some new restaurant, right? On this new weather, new day of the week, and so on, right? Whether what kind of action would be. So that's the kind of machine learning problem. And you might say, okay, what type of problem it is? Well, we are predicting yes or no, right? So these are only two values. So these are discrete values. So that means this is a classification task. Classification. We are trying to classify what to do, right? The previous one, this one here, this was a regression task, because we have potentially infinite values of x, right? Potentially values of y as well, right? So here we have specific values here. Yes, we do have some we have some floating point values here. Yes, but here the answers are discrete. So that's one of the core difference between these are both supervised learning tasks. One is discrete classifier, this one is discrete, this one is floating point continuous value, so this is a regressor. So, okay, so there's lots of issues, right? So the thing is, you have these 10 features, and there's multiple choices, to 2, 2, 2, 2, 3, 3, 4, right? That's the only code in this book, by the way, right? There's not going to be much more code. Maybe I'll make this a little bigger, right? So you can see there's 9,000 potential values, right? Again, to learn, right? But we only have 12 restaurants, right? So yeah, so what kind of algorithms can be there? One of the typical ones could be a decision tree, right? So it goes through all these values, so sort of makes a tree of choices, binary choices, right? Whether you do something or not do at certain condition. So basically generates if-else statements, sort of multiple ones, on to provide a strategy what to do. And that's why the beauty of decision trees is that they are quite visual, right? So very well, maybe you have, so this is an example of visual decision tree. So this is what we say, okay, we check patterns, there's none, maybe some full, and we can decide on strategy. No, yes, or then maybe we wait, right? We check, okay, if it's full, right? If there's none, there are no patterns, that sounds very suspicious. As there's some, we go eat. If it's full, right? Then obviously we cannot, it's full, right? So we have to wait estimate. If it's over 60 minutes, we already know it's forever, it's hopeless. We check if there's alternate, right? No, yes, and so on and so on. So basically a lot of choice to make. Eventually we arrive at the leaf of our choice, of our tree, and we have a model. So this means we have 1, 2, 3, 4, 5, 6, 7, 8, 9. In this particular case, this decision tree is actually using all features of our table data, right? I think 3, 10, 9, right, or 10. So, but it's not necessary, it doesn't have to be. Model could be simpler, and also it could be utilized more and more of these. So yeah, so there's a pseudocode, I'm not gonna run it here, right? I'll show it maybe later on in an example. Now, so yeah, so again, very powerful technique, and it works on pretty much many features, right? So again, the algorithm, I'm not going to go in detail on this algorithm, but it's not a deep learning algorithm, it's just a regular decision tree. It does not, it can work with multiple features. That's one of the positives, right? But of course it can also tend to overfit as well, right? So you can overfit with this very easy, right? So yeah, so because again, remember, we are not trying, again, we already know the answer for our training data, but we want to generalize to our on-scene data. Overfitting is always, so the more complex you go, the higher the risk you will overfit, and your model will become basically just a fancy predictor for existing data, which is useless. So there's lots of ways of doing this. So there are ways of improving it. Basically, sometimes we want to, there's a lot of things we might encounter problems. We need strategies for dealing with missing attributes. What to do with continuous attributes, right? Maybe we can split them into discrete values, right? Maybe we have multi-valued attributes without meaningful order, meaning zip code, for example, right? An idea being the zip code 91002, right, and 103. Well, the order there is not particularly specific. It really should not be a numerical value. Maybe it should be really discrete, right? So there's a couple different things, couple issues with these, right? So advantage is the decision trees are easy to understand and scale to the large data sets. So again, the greedy search, again greedy, remember from our algorithms course, right? They can be unstable, small change in data can lead to significant changes in structure. So there is a way of dealing with decision trees. Some of the solution is to basically use something called random forest model. What does it mean actually? You make multiple trees for partial data in your data set, and this sort of have this voting basically. It's like multiple trees, multiple voters, right? It's called ensemble learning, and this actually works very well. It's very common in machine learning, using ensemble learning, meaning you run multiple models and then you choose actually out of all these, you have some procedure for deciding on what best value is. So yeah, right. So then we come to something to the training and need for training and test set. What do I mean by that? Well, we do not want to bias, we don't want to influence our models by our answers. So this by itself will need we want to separate the trainings data into training set, right? We want to evaluate models, right? And then we will want to have a test set to evaluate the chosen model to see how well it performs under, for this particular model. Yeah, there's also could be a validation set, right? So validation set and test sets, well, they actually can be related, right? Meaning sometimes you just skip basically use one. They're not both. Basically, you don't use both, but technically you can divide them, right? Meaning, so when you're evaluating this set, right, and then you have the final test set. Sadly, we always dealing with limited data. So what we do is the validation set is actually used in interesting way. Is we use something called k-fold cross-validation, meaning in our training set we take a small subset as for validation in each fold. So maybe we call this 10-fold cross-validation. So your training set always, we do our model 10 times and 10% of the data are used in each run for validation, right? So that's another thing we can do, right? So again, this process can be qualitative. The selection, choosing what to use, machine learning field has many different algorithms and whole families of algorithms. So it's one of them is just it's like going shopping, right? But you have or going to a all-you-can-eat restaurant. You have lots of algorithms, but this can be very exhaustive process, right? But oftentimes what I want to touch on is problem-specific knowledge. So you can go in completely blind, which students tend to do. Meaning you just run models, okay, see what something works, but sometimes you want to make some questions, some human domain-based knowledge, problem-specific knowledge on whatever you are trying to predict, right? So that might be very helpful. Like I said, typically also students want to do something predictive on stock market, for example, in finance, without knowing actually how stock market, at least some basic ideas behind it, for example. That's just one idea, right? So idea is how do we select these models? Well, we need some sort of a way of measuring, of course, our data, right? So there's a couple of ways. We do, of course, there's two typical patterns can be, do I have these patterns here? I don't think I have them here. Well, you can expect either that you start getting, what you will see this at some moment in as your models get more complex, your training data will start you'll start getting more errors. So typically you start with an underfit, at some moment you start to overfit. So it's a problem of set. It's like in that joke about banana, all right, when somebody was drunk was asked how to say banana, police asked them, they said, okay, I can spell banana, but I don't know when to stop, banana, right? So here, not a very good analogy, but idea being that you need to stop at some moment, right? And so we can sort of measure our error rates and see when we are actually, our training sets are generating, well, we start going, it's getting worse, right? So, yes. So there are a couple different curves, right? And there's also something interesting. There is not only error rates, right? But also we have something, right? So there's different ways of errors. For example, right? So mistaking non-spam for spam, right? Is probably much. I'm talking about email filters, right? Can be much worse than reverse. Meaning you get some occasional spam from somewhere. Some prince is giving you money, right? You can probably do it yourself and deal with that spam. However, missing some serious email that you really had to get your scholarship or something, which was maybe because of money aspect is flagged, a bad algorithm flagged as spam, right? You don't want that, right? So you probably in a spam classifier, it's a classifier type, right? You want to have to error, meaning let some spam through, but not make any don't make any false positives basically. So for that reason, sometimes they use something called you reverse the error as a loss function, right? Meaning there's a function for loss, and it's not strictly just a simple reverse function. There's a formula for it, basically, and you want to generalize this. So basically, right? There are different loss functions, but the core idea is basically you minimize the expected loss across all possible inputs, right? So that's what we are measuring when we look at these training epochs, right? The loss function, see, it should be decreasing, right? Again, regularization, another core idea, right? So we want to make our function basically be more regular. So what does it mean is we are, well, it's basically making functions more regular, basically, right? So again, this is could be helpful using minimum description length, right? So, and I mentioned already, a core idea is hyperparameter tuning. So this means that basically we can do something hand tuning, which is basically trying yourself. But typically what we do is we use something grid search, which is a fancy way of saying we supply some parameters with discrete values and we test these combinations. However, the bad news is that sometimes you have too many hyperparameters, too many possibilities. Then what can you do? You can do some random search. You can do some sort of some optimization. So you can say you can optimize the actual hyperparameter tuning. As a machine learning, you're applying machine learning to machine learning itself. Kind of funny way of doing it, but that's actually is also usable. So to tune the parameters for your algorithm, you apply machine learning to it. But so this is a big field of research. Now we can touch, right? So a foundation, we go back to basics, the theory of learning. So how can we be sure that our learned hypothesis will predict previously unseen inputs? So how do we know that? Well, there are various theories, such as computational learning theory, right? Concern how to learn best, basically, which deals with that area. Now I'm going to skip this, right? Learning decision trees. On yes, so linear regression is a model, right, which basically supplies a linear function. We'll see this in a practical examples in a moment, so I'm not going to touch on it. So you can also do classification also with it, actually, right? But so here's an example. So in this example, again, we have a problem that these data sets, a linear regressor will make the same predictive function, a linear function, ax plus b, right? As you can see, that all four sets, they're completely different, right? You have a parabola, you have an outlier, which is linear but outlier based one, and you have some random sets. So here's a question from me to you guys. Which one do you think linear function is actually best used? Well, I would say that this actually is a linear process, looks like a linear process with some noise. So this is actually where linear regressor would be helpful. Here, right, you probably have to do some pre-processing, and then you actually have a different linear regressor to get rid of outliers, maybe, if they're not important. Sometimes they are. Well, of course, these two cases you see linear regressor is not the right function, right? These two again. So that's the problem with linear regression, that it is, it will give you always answers sometimes when it's not really needed, when it's not really appropriate. So now some things, some techniques such as gradient descent, right? It's a general purpose optimization, right? How to move when you are building a model inside the model, how to minimize the loss function, basically. That's a very, very commonly used, right? Another concept is multivariable linear regression. Mean is, of course, instead of single line, like a single x, we can have multiple x1, x2, x3, x2, x4, and so on. Right. We can also add some hard thresholds to the functions. Logistic regression, you can turn a linear classification to logistic regression, right? And yes, we can also have non-parametric models, meaning we don't have a fixed size set of parameters, but just have a whole bunch of parameters, right? Right. So they are very flexible, but again, they have a problem that you need more data, more storage, actually, right? And also they might not generalize well, right? Again, so then there's something called nearest neighbor based models. These are typically used actually in clustering, actually, right? But they can be used also for classification, meaning looks for something closest to something, basically, right? I will see about this also in some examples, right? And locality sensitive hashing, right? See which maybe you want to find on nearest neighbors based on hashing, actually. Very interesting technique. You can read about that one, but again, this would be too deep for introduction, right? Non-parametric regression on support vector machines. This used to be a major, well, it still is, but not much since the advent of in improvements in deep learning. Support vector machines were about 20 years ago were a huge area of interest. And they thought that this was a way to proceed. This was where progress was being made, right? They perform very well in higher dimensional spaces, right? They have use some nice tricks, something called kernel trick, right? If you cannot allow data that is not linearly separable in original input space, we can separate it in higher dimensional space. Very interesting trick, but they don't perform very well on large sets, right? So there's kernel trick, which is kind of cool. And I mentioned already ensemble learning, another idea that you use diverse models or multiple similar models to make predictions. So you combine them by voting or averaging. And it's funny thing is, it might seem kind of strange. If two, let's call them idiots or maybe not so smart models, if they make predictions, are they really going to be better than one good model? Well, it turns out they can be, right? It's been proven that actually, even if the model has it can add a slight something, a little bit, even if this seemingly bad model adds something little bit to ensemble, it will still improve the whole ensemble, right? So it reduces the risk of overfitting, right? Of course, the problem is, here's an example. You had 5 classifiers, right? You can actually achieve maybe 90% by majority voting. So, assuming they're independent, right? Of course, in real life, no model, and also not agent, right, are not completely independent, right? But principle applies. So there are a couple of interesting things, right? So different sets, there are all kinds of tricks. These are all kinds of tricks of trade, right? Random forest, right? More diversity than the ensemble, stacking, lots of things, boosting, also prediction accuracy of set of weak models by combining them into a strong model, right? And so multiple approaches. Now, one thing we did not cover, this is more of again terminology, online learning. So what's the difference? We typically deal with machine learning as a batch learning, meaning we have data, we do something, we train the model. With online learning, data is coming in over time. So it's a continuous process. So the question is, what do you do? The simplest way you can do it, you can always retrain the model on all of the data, start from scratch, right? Might be a viable approach. However, if you have a large, expensive to train model, that might not be. So you need something called supplemental training or maybe fine tuning, right? So we have some extra issues, extra challenges with that. And now we come to actually practical issues, steps of how you would develop a machine learning system in real life. And I've had multiple students in my bachelor's thesis work do something like that actually. So of course you have to define a clear problem, right? You understand what the project is, what the data is, and how you will measure the success. You collect the data, you prepare it. In fact, this is usually 80% of the work, this data collection preparation. Do not underestimate this collection part. And then you get to exploratory data analysis. You explore the data, maybe you add some new features using feature engineering, and then you get to the fun. So this is the fun part. The model selection, when you're playing around with different models, can be quite rewarding, because you're getting results, you're getting feedback. And we human agents like feedback, right? So this, of course, you find most effective model, you train it, right? Of course, you retrain it maybe, and you adjust it, and then, of course, in real life, you have to also deploy it in prediction, where it can actually be useful in some company or some organization or to your own projects, right? And that's not all. You also have to perform maintenance and monitoring. If it's an online model, of course, if you have to monitor how it's continuing learning, maybe you have to retrain it again. So, but that's a general framework. So, identify problem. So, are you, for example, a person says, I want to know the price of a house. So you might say, okay, that's a regression problem, right? Well, maybe this person also actually wants a model to know when to buy or not buy, and that is a different problem. That's classification problem, to be or not to be, right? That's a classification problem. So is it continuous value needed, or maybe it's actually discrete values? So again, you need to identify this. So that's always starts in real life scenarios, and that will be told you by many professionals who work in the field, that they actually what are you trying to solve, right? Are you asking the right question, actually, basically, right? And then, of course, you can identify the components, and that's, of course, is all. You can choose labels, and you have a well-formulated problem statement. Okay, so data collection, lots of data collection. I mentioned this already, lots of work. And again, another thing I want to say, I mentioned this before, that domain knowledge. This means you learn your actual knowledge about the field. Machine learning is not an island in the field of knowledge or science. Machine learning improves when it works in conjunction with whatever problem it is trying to solve, right? So you might know, for example, house selling, right? You might not need just asking price, right? Maybe house size, number of rooms, amenities, age, and state of repair, for example. Maybe neighborhood, right? So, of course, I did not even talk about bias again in this example. So, exploration, of course, might be useful to realize what's something wrong with the data. John Tukey, very influential in exploratory data analysis and data visualization. Model selection we already talked about. Right, trust. Again, you need to verify, of course, validate, of course, operation, monitoring. It's all important steps. I want to also get to show some things in action. I don't know how much time we have here. This is no, we have some time. I want to do this in an hour. So we saw. Let's go back to this whole thing. The beginning. Or actually, we'll have this here. I'll show you here. There's some nice historical and bibliographical notes. I recommend you see if maybe some of them are interesting. But I want to show you this. There's some nice books, by the way. I recommend this one, Hands-on Machine Learning with Scikit-Learn, Keras, and TensorFlow, by a former YouTube and search engineer, main one, I guess, right? But there's also a new one with PyTorch as well. And I want to touch on this fantastic library by Python. Amazing library. And also, why it's amazing, it also provides a really nice, I'll show this, right? It shows a very nice cheat sheet. Basically, you start a sort of a way of getting yourself familiar with the problem, right? So you start here and you say, how much data I have, how many rows of data, how many measurements. If you have less than 50, you probably need more data. Well, sure. And then you say, okay, I want to do something. Are you trying to predict a category? Meaning, answer yes, no, red, black, blue, or apple, banana, and citrons, and so on. That means, of course, classification most likely, but then the question is, do you actually have answers? Well, do you have the labels? If you do, you go into classification task, right? And again, it's kind of funny that actually, if you think about it, LLMs you might have heard of, which we'll talk in in a few weeks we'll talk about large language models. They actually are, in a way, they are a type of classifiers. They're trying to classify, predict next token, basically, right? Numerical discrete value, actually, right? So clustering is when we don't know what we have, we just want to group it. Then we have regression, which is numerical, continuous quantity, continuous value. And then we didn't talk much, the chapter does not talk too much, but we might need to perform something called dimensionality reduction, because there's this concept called curse of dimensionality, right, which I did not mention, right, in data science and machine learning, right. Basically, when you have we don't have enough data and we have we have too many, we have a lot of, for example, genes, right? Or field or space, basically, right? Or data set, it's too sparse, basically, right? We have too many features, and then we don't really, it makes it really hard to build a meaningful model. So that's something we can add it also to the book, right? So here are some takeaways. Maybe I should add this here. Yeah, curse of dimensionality. That might be something to consider. Okay, but yeah, I mentioned these books in library, and also I made some supplemental books. We have some time. Let's do a simple live coding. Let's see how it goes. I will save this notebook for you guys. Some changes. Well, let's see this in action for something to play around with. Assuming, yes, everything works. Now we go to live coding. And let's do, not from scratch, which is also a very nice one. I like this one also I made. But let's do this one here, introduction. So the first one, right? And we will utilize scikit-learn, right? Which is, we utilize scikit-learn. Let's connect. Library, right, which I mentioned already. So we'll use NumPy, which is a numerical computational library. Matplotlib for visualization libraries, right? And this is, of course, is a numerical computation, basically vector matrix tensor operations. And by the way, tensor is just 3D and multiple dimensional way of storing data, right? And let's take a look, see how it works. Last time I checked, it works. Maybe it works this time, hopefully. And yeah, so remember, again, we have what types of learning? Supervised and unsupervised learning, right? And we have to perform a training or test split. So let's do a make regression. So we imply the make regression from data sets, right? So this is we're gonna make some data. Let's see how it looks like, right? So train and test, right? So what we did is perform something called train test split. So what we did is, so we split our data into 70% train and 30% test, right? Typical range is 70 to 90 for training, and so on accordingly 30 to 10 for testing. I would say it's more common to do 80-20, right? So very simple, right? So you have some data and we simply here split it. Simple stuff, right? So again, tuples, right? So this comes from scikit-learn, and you don't have to do it yourself. I do have a notebook for doing it yourself, right? But there's no need. So again, generally, while I do have a notebook on doing split yourself, generally you want to let the library handle the split for you. So this is a case, right? Basically, we split the data you have some training and testing data, right? So again, why do we do this? So these red dots don't influence the model when we are using the blue dots to learn, right? So let's look at some overfitting examples, and maybe not so overfitting. So underfitting is model is too simple. Overfitting, model thinks too much of itself. Let's take a look. So, okay, here we go. Yeah, so we have some data, right? And as you can probably imagine, we had some polynomial, right? What do we have? The sinus function with some noise. So this is a truth. So we sort of cheated. So here we are all-knowing creature, right? We know the function used, but in real life we would not know this, right? But so we know it's a sinus plus some randomness, right? Yeah, so sinus is some randomness. So you can see here how a linear regressor would just simply draw a line. And again, why is the line exactly like this? Because, well, that's what minimizes the error, right? But again, it's probably not very useful. So how about polynomial? Degree 5 looks really nice, right? Looks more like it, right? But we know the problem is, at some moment, if this is real sinusoidal function, right, this polynomial will start to break away. So that's something you should be aware of, right? Degree 15, this is almost, not certainly, but I would say 99.9%, this is overfitting to existing data. It's starting to basically fit to what we have, but not what we want to get. Yeah, so crucial, right? So again, so think about this. Think what will happen when we supply some new data outside the range of existing data. Yeah, again, these polynomials will not work very well. So decision trees are pretty easy, right? So we have two blobs. We made two blobs, right? And a classificator will do a nice fit. It will, of course, here we didn't actually do a training, but basically it will predict perfectly, obviously, because it was such a simple, because we made two blobs. So again, our test or incoming data was very simple. We simply supply two blobs, right? So it'd be interesting to see what happens. I recommend to see what happens if you do 3 centers. What do you think will happen? Let's try this. Will it work? Indeed, it works fine. So how about 4? Right? So these, of course, are fake data. Right? And now, of course, right? If I do like maybe 8 blobs, we will start to overlap a little bit, right? I expect, yeah, you see the problem. Now we start getting problems. So that's, of course, with decision trees, there will be problems. When you have overlap, you will start to encounter problems, right? Because it's inevitable. We have 2-dimensional data, right? And we're trying to predict. We have x and y, right? Or x is basically 2-dimensional, right? So, right, so our classifier, right? So, and the color is our predictions, basically, right? So, again, so let's go back to maybe something like 5, which will probably still work. Yeah, but already you see the problems here already. 1, 2, right. And you can see here, by the way. So this is the beauty of decision trees. Decision trees provide you with a clear answers how you should work. So here it says 40, 40, 40, right? Samples, right? Originally, if it's x2 less than 1.2, this is sample, this color 3. I don't know which one it is. It's probably x second feature. It's probably this one here. Yeah, minus less than minus 1 to 0.5. Yeah, here. Yeah. Okay, somewhere here. So this is all this color, basically. Then, of course, things get harder. So notice, by the way, an important point is that we can repeat our choices, right? We only have 2 features, x, two dimensions. But we can keep asking answers on the same dimension, right? And we eventually arrive at the classificator, right? And you can see how it's not completely clear, not perfect, but Well, you can see the examples here does not work perfectly, but that's fine. And now finally we get to clustering. So without labels, right? Without labels, right, it will perform clustering. Can we have colors here actually? Predict on color labels. Why doesn't it work here? It works. It should work pretty well. So we know. Okay. So the thing is, with k-means, one of the key idea. K-means works pretty good if we know how many clusters we expect. So here we know 3. So if I change it to say maybe 16, right? 6, let's take a look, right? It will actually perform 6 clusters, right? Unfortunately, the coloring doesn't work on this example. I would want to show you the coloring. Scatter plot, maybe it will, no, yeah, everything works fine, yeah. So here we see, yeah. So you see the problem here, right? So if I say 6, right, it will create these clusters, right? It's like the joke about the accountant. Somebody told him, what is 2 plus 2? Well, the accountant says how much you want it to be. So with k-means clustering, it's the same joke. You say you want 10 clusters, you will get 10 clusters. In extreme case, you have, let's say you have 300 samples, you can make 300 clusters. That would be a model, but completely useless model. Basically, every sample by itself, completely useless, right? We can do it by hand, basically, cut everything separately. But yeah, so again, notice, so again, 4, right? We should have nice clustering here, right? Yeah, now everything works very nicely. Again, if I make it 8, it will be increased. If I say 3, right? I'll have 3, right? But so again, it clustered this as whole, and this is the center, right? So basic idea of k-means, they are so-called centroids, right? Where there's some dots based on some air, which are basically, you assign values based on these centroids, and these centroids move around actually when it's being built. So let's go back to 4, and then we can finish this lecture. So again, if you know how many clusters, it will build this. So we have really good performance in this case. So you saw some simple examples of all 3 major algorithms. We learned how to do train test split, overfitting problems, and we performed what? We performed regression, various regressions. The most popular, of course, is linear regression. We did classification using decision trees. We'll do other classification tasks in the following lectures, and we also perform k-means clustering. So those are the 3 major areas of research, right? So classification, regression, and clustering. All right. So thank you, everyone, and I'll see you live in a lecture in a little bit more over a week. Thank you, everyone.